Welcome to the TWIML AI Podcast. I'm your host, Sam Charrington. This week on the podcast, I'm happy to share just a few of the nearly 20 interviews I recorded earlier this month at the 33rd Annual NeurIPS Conference. If you've been waiting for the TWIML pendulum to swing from workflow and deployment back over to AI and ML research, this is your time. We've got some great interviews in store for you over the upcoming weeks. Before we move on, I want to send a huge thanks to our friends at Shell for their support of the podcast and their sponsorship of this NeurIPS series. Shell has been an early adopter of a wide variety of AI technologies to support use cases across retail, trading, new energies, refineries, exploration, and many more, and is doing some really interesting things, but don't take it from me. Microsoft CEO Satya Nadella recently noted that what's happening at Shell is pretty amazing. They have a very deliberate strategy of using AI right across their operation, from the drilling operations to safety. Last year, the company established the Shell.ai Residency Program, a 2-year full-time program which allows data scientists and AI engineers to gain experience working on a variety of AI projects across all Shell businesses. If you're in a position to take advantage of an opportunity like this, I'd encourage you to hit pause now and head over to Shell.ai to learn more. Once again, that's Shell.ai. And now, on to the show. All right, everyone. I am here in Vancouver, British Columbia at NeurIPS, and I've got the pleasure of being seated with Mohamed Sidahmed. Mohamed is a machine learning and AI R&D manager at Shell. Mohamed, welcome to the TWIML AI platform. Thank you, Sam. It's really excited to be here today. Chilly Vancouver. We're very delighted to be in NeurIPS this year. It's a pleasure meeting you. It's also an exciting time to see all the latest and greatest in the cutting edge technology in this field. Yeah, absolutely. I am also very excited to be here. This is my third NeurIPS, and in fact, I love Vancouver. The Vancouver Convention Center I can't think of one that is more beautiful and, in as scenic a context. So I'm really excited to be here. And happy to see you again. You, of course, were at TWIMLCon, AI Platforms, and it's wonderful to get a chance to actually get you on a microphone and get a sense for what you're up to at Shell. Shell actually has a couple of papers here at the conference, right? We do. Actually, we have a couple of conference papers being presented this year. We have one actually deal with least squares for seismic interpretation, and the other papers, which is basically, we call it a FaciesNet. This is a new architecture we designed for our kind of well-log classifications and rock typing. So it's part of the geophysics community and how we're applying machine learning for physical systems. Awesome. And so for this conversation, we're going to dive into the FaciesNet paper. But before we do that, the least squares paper, tell me a little bit more about that one. That is actually our kind of internal R&D approach for how we use machine learning and deep learning specifically to actually generate an equivalent kind of workflow processes to the physics-based approach for full-wave inversion. If you think about how the geophysicists historically been doing the all imaging using seismic data to try to identify different types of zonal interest areas. So we actually identified a huge breakthrough in terms of time-saving computational simplification relative to the conventional approach. So you mentioned phase inversion. What is that specifically? That's typically like when people actually have a seismic survey to measure what is the prospects of finding hydrocarbon on the subsurface. There is an imaging process that actually generates seismic images from this kind of seismic data. And this is a process of taking all this data and trying to generate a high resolution image where you can pinpoint where is your kind of area of interest look like. Mm-hmm. Historically, it's been a very computationally intensive. This is required almost a month amount of effort. And now a lot of traditional high-performance computing has been applied to these types of problems. Indeed. And that's quite frankly the highest investment in the energy business. It's not very common to see
a data center with almost 20, 30 petaflops of computational cycles in a data center in an oil and gas company. And that's actually one of the things we rely on, even for training our deep reinforcement learning models for this type of applications.
I don't think we got to the inversion, the phase inversion. Where does phase inversion fit into that scenario?
So this is typically when we take the migration of waves into the subsurface of Earth and trying to reconstruct an image based on these kind of reflectivity of sound waves that goes to penetrate the subsurface. So basically you reconstruct a whole image based on these reflectivity of sound waves.
Oh, got it. And so this paper then, with all that as context, is showing what?
Basically, it's showing how we can computationally efficiently reconstruct the whole problem using a deep learning framework approach. So relying on sequence models to be able to generate these type of image construction and using image recognition to be able to classify what type of interesting zonal areas within these images.
Oh, nice. Nice. And you mentioned reinforcement learning. Is reinforcement learning a part of this particular problem, or something that's used more broadly or in other areas itself?
Actually, we're using it in different areas. Typically, one of the issues regarding the space that we work on is the limited of label data. So it's a very high uncertain environment, and typically to be able to confound it in a well-defined simulation is not applicable all the time. So we're trying to complement that with novel approaches of defining what is the physical boundaries of the system look like in order to be able to use reinforcement learning.
Okay, interesting. And so the other paper that is presented here, the FaciesNet paper, that's one that you worked on personally?
Indeed. Yeah, this is actually a very exciting paper. We had our kind of whole team, including one of our summer intern from Stanford, Earth. She worked on this paper extensively with our extended team. And we're very excited actually to come up with a very novel way of designing a new architecture for how we use sequence model and recurrent neural networks to be able to basically break out the benchmark, the best in practice standard in the field for how you basically classify these different type of rock facies.
Okay, so this paper, like the one we discussed a second ago, is also kind of focused on this exploration problem.
Indeed, that's correct. So this is as you think about the whole life cycle of how quickly you can maturate your hydrocarbon discovery. This is typically several months, could be 9 to 12 month time frame. And by introducing how we can apply machine learning to this type of a problem, we're actually aiming to reduce that, what we call cycle time, by almost 50%. That's why we're trying to tackle the problem by identifying these bottleneck areas, which whether is computational intensive or require massive amount of data and human effort to be able to use human judgment to classify and make some sort of an inference.
And so this paper, you're proposing a new network architecture here, or?
We're actually proposing a new architecture by combining two different type of approaches. We're using actually a sequence model to be able to actually detect what is the sequence of these different facies type. And for people who might not be familiar with that, typically on the subsurface of Earth, they are kind of an alternation of sequence between, for example, clean sand, could be a clay, a dirty sand, and different types of facies type or lithology types that usually we penetrate. And you can think of this as typically a way of identifying where is the area of interest that you would like to target in your targeting zone.
The images that are forming your input data are, I'm envisioning them as like cross sections, I guess, that are, or a stack of these different types of facies that appear in a sequence, and you're trying to determine or be able to predict the different layers?
The novel way actually we deal with this, typically the features are representing geological features. This could be something like a gamma ray, neutron porosity, permeability, and so forth. But what we actually discovered that for the conventional method that trying to use machine learning to solve this type of a problem, they quickly ran into an issue of not taking into consideration the sequence nature and overlapping by trying to predict the next type of label of a facies without taking into consideration the previous one. So what we have done is we actually converted these different well logs. It's basically like a porosity log using neutron gamma rays to actually as spectrograms. So basically now you're generating an image with a texture feeling that represent the sequencing based on depth. So we're using a short-term Fourier transform to be able to convert all these kind of log measurements into a spectrogram with a texture representation. So now you have an image to train based on.
This spectrogram-like image is the output of the thing that you are, that this paper is talking about, or it's the input?
That's the input. So the nice thing is usually we have geologists and petrophysicists who actually have a labeled sample based on very limited amount of cores. These are samples being extracted from the earth, and they were able to actually delineate what each type of label represents. So we have some of a small amount of labeled data by subject matter experts. But the input for this model is the spectrogram image that we actually generate based on the measurements.
Okay, and the spectrogram image is it based on the same type of imaging that we were speaking about with the previous paper, the sonar type imaging? These
are different. Okay. This is actually one of the, to my knowledge, this is the first time we actually convert some of the well logs data. That's actually can think about it as a depth-based measurement to reflect what is your gamma transfer in Earth to an actual image and use that as a training input for our model.
Oh, got it. So you've got these walls in place. You've got something that is going kind of up and down the walls, a sensor head, and you're taking measurements of, you said gamma rays and neutrons.
Right.
That sounds like such science fiction.
Right. So exactly, you're spot on. So these are the typical measurements. Every time a well has been drilled, you actually take a logging measurement. So basically, you would like to measure the resistivity around the well, which is basically give you a different kind of representation of what type of rock around that. If there is a high reflectivity, this is likely to be a sand. It could be a clay. It could be some sort of a mixture, like a cemented sand or so forth. So in this particular situation, we have about 6 different type of what we call physical properties. We use it as an input for our model after converting it to the spectrograms. And as a matter of the outcome, which we're trying to predict, is what type of facies we're actually looking for. In this particular situation, we have 5 different labels, so it's a multi-class classification. But that's the unique aspect. Historically, what most of the state-of-the-art technology in that field, people are able to actually predict at most 2 or 3 classes, and they kind of misses the majority of other relevant classes because of either the distribution factor is very low, and the high distribution of a class that's dominant is typically to be classified correctly. And this is actually something we're very careful about, to be able to use our balanced accuracy as a measure of evaluation, not the general accuracy for the model.
Maybe for a little bit more context, what does being able to predict the fascia type allow you to do?
So this is actually allow the whole field development plan to be able to develop your field, how you basically determine where is the chance, the likelihood of finding the hydrocarbon deposition in certain area, where do you place your future wells. So this is based solely on exploration wells. Usually you have only about 5 or 6 wells being drilled at the early phase of development for your field. And the intent here is you need some sort of high accuracy, high fidelity that would give you confidence to design the plan for future field development plans. So for example, in certain areas, you might be drilling up to 200-300 wells, and you need to be able to identify where exactly you place that well. So you'd be only interested in one type of facies type. So this kind of clean sand, that's where the reservoir is placed. And being able to predict that area or that type of facies with high accuracy has a huge implication down the road for your field development.
Well, where this paper fits into the process as being a little bit further along than the previous paper. The previous paper, you are doing kind of, sonar based geological studies to try to get a lay of the land generally before you might put these exploratory wells in, and then your next phase. And I'm sure I'm dramatically oversimplifying this, but
that's absolutely
the next
correct.
phase might be, hey, we'll deploy a few wells to get a sense for what it actually looks like down there and get some sensors underground, and then that then gives you the information that you need to figure out where to deploy your next set of investments, which might be much larger in scale and much more expensive.
Absolutely, you're exactly correct. So the first paper we talked about is part of concept selection evaluation. So how do you basically have some sort of economic assessment evaluation and confidence that there is a likelihood of potential value in that prospect. The second paper we talked about is a decision has been made to go with a specific field, but you need to be able to maximize your development plan down the road in the future.
And so the innovation in this paper again is kind of a transformation of the features into this
image
spectrogram,
type.
this image type, and then applying sequence models to that image type to get state-of-the-art level prediction of the fascia, the multiclass fascia classifier.
Exactly.
Okay. Let's talk a little bit about the development of the model and kind of what drove the eventual direction of that. So it sounds like, one of the key inspirations here was that, hey, this is kind of a sequential, a problem that might lend itself to a sequential type of approach. Did you discover that, or is that where you started?
Actually, we had an iterative kind of experiment. This is part of an ongoing research project in our portfolio. And we're very kind of focused in terms of trying different architectural design. But we actually have a preconceived notion that one of the limitations of the published literature in the field is you actually overlooking some of the sequence aspect of how these facies are sequenced in the physical system. Typical to, for example, speech recognition, where you need to be able to predict what is, for example, the next word or the next sentence based on the sequence of your previous text. So that actually inspires us to think about how would you construct a sequence model that would take into account what is this kind of overlapping nature of different facies, that the way it actually manifested itself in a physical system. So we looked into the recurrent neural network architecture, and we tried to determine how we can actually leverage this sort of spectrogram into that notion. But in that particular situation, one of the primary limitation is it would only allow you to train on a single kind of image texture structure. And this is typically have a limited amount of information from a practical standpoint for geophysicists and geologists to make that sort of an inference. So think about one physical property I mentioned, like, for example, gamma ray, has a very good indication of what facies type is that. So by taking that initial measurement, that first kind of input feature, converting it into a spectrogram and using it as an input, now we're able to generate a sequence model that's only solely based on one feature representation. Mm-hmm. But we actually went a step ahead and we said, now we need to think about training based on multiple images, multiple of these kind of spectrograms. And in this case, we actually have to adjust our network structure to have an encoder-decoder upfront to be able to take these kind of multiple input feature set and use it as a feed forward to our recurrent neural network. So that's actually one of our kind of a breakthrough moment of saying, now we are able to include additional feature representation. And it's also very kind of dynamic. In certain areas where you want to generalize this model, you might not have the same set of input features, but our architecture is very flexible to allow people to say, for example, you have feature X that's not part of the existing input for the model. It's very easy to incorporate that and use the encoder-decoder layer to be able to actually use that as an additional input.
So the input to the encoder-decoder layer is multiple images, each corresponding to one of these features, gamma rays, neutrons, etc.
Indeed.
And so you're transforming these n dimensions of images to some kind of single space, and then using that as your feature set for the sequence model?
Correct. That's exactly. So we have initially a 5 hidden layer for doing basically the encoding for encoding decoding, and the output is fed into a sequence model, Rn and N, with 2 layers. And then the last layer is just a softmax, which actually output which kind of facies is that output, whether this is a clean sand or a dirty sand or cemented and so forth.
The spectrogram images, say one of the images, the gamma ray one, is it a single channel image or a multi-channel image?
It's a multi-channel image, and you think about this is part of the construction of the depth sequence that's on the initial gamma ray. So you will have basically the input when you generate the spectrogram is going to create this kind of a multi-channel image that was used as a feature input for our model.
Meaning the channels are the time series of measurements, or because I thought we would have gotten away from the time series by doing the Fourier transform and getting to a frequency domain.
That's correct.
What would the channels represent then?
So this is a 3D channel. So it's a 2D image, but we actually project it as a 3D input for the model itself.
And so, when we think about using images as inputs, the obvious thing that comes to mind is a CNN or some type of model like that. Are the sequence models that you're using CNN type of sequence model, or is there some kind of, did you explore that direction? Or
we explore that direction for this particular actually application. This is a bidirectional recurrent neural network. And the reason being that is, especially when you have a limited amount of training set for a number of these images, the performance and the stability of the model is actually much, much more stable and able to converge, rather than expecting, for example, a CNN with a very large amount of labeled data. So one of the primary reasons that dictating the selection of the architecture we used is how much amount of data we have and how much labeling, actually accurate labeling for these data is available.
Okay, got it. Makes sense. How do you construct your performance evaluation? You mentioned that you're looking at a bias-weighted metric. Did you have to iterate to that, or is it obvious what to do there?
In fact, we looked at different types of loss evaluation functions. So we looked into the general accuracy and the balanced accuracy, F1 score, and so forth. And one of the things that's typically reported in the literature, people actually look at the accuracy. But as I mentioned before, the drawback for that is you always correct with the predominant class in your kind of outcome. And in this particular situation, we're very kind of focused about taking that kind of balanced accuracy in place. So we came up with our drive metric based on multiple performance indicators to come up with more a human interpretable and also provide some rationalization for the human expert to interpret that and take it into consideration forward. But it's been more an evaluation, and to compare that as a benchmarking mechanism, we actually compared our FaciesNet performance against several of the state-of-the-art technologies most people use, for example, naive-based classification, random forest, and other types of model to be able to actually do the classifications. And actually the paper have a very decent representation, almost close to 9 or 10 different algorithms that's been reported and showing the performance difference.
Okay, and what was the performance difference? How big a deal was it?
It's quite significant, actually. The highest accuracy rate that's been reported is about 72%. So we're actually above like 75% accuracy, and this is across all the 5 different classes. The most actually people get it right for like 3 classes out of 5. So we are able to accurately, correctly classify more number of facies type than just focusing on the high representation of classes available in your training set.
Okay, cool. Where does this direction of research take you? What's next in pursuing this work?
One thing actually we're very passionate about, we always active to outsource some of our architecture. This is not the first paper we outsource the code to the community. In fact, we have a GeoDNN outsourced library. It's a model that we developed for the geoscience community, and it's been contributed to our public GitHub. So we're kind of actively trying to drive this as a mainstream application for machine learning within the physics community in general.
And so is this one already up on GitHub?
It's actually it's on its way in GitHub.
As we speak, any moment now?
As we speak, right now, as the paper is being presented, this should be available for people to actually start using and actually contribute to expansion of this approach.
Who are the folks that you expect to be using stuff like this? Is it primarily academic research labs or other energy companies, or?
It's a joint, actually, because quite frankly, we are very optimistic about the level of collaboration between industry and academics. As I mentioned, the outcome of this results is a combination between our internal R&D research team and also some of our people from the academia who were part of that research project. Moving forward, the intent here is to make these as part of industry standard. For example, there's a consortium of open subsurface data universe platform for experimentation and trial that's been signed up by more than 83 different academic institutions and industry partners to work on improving different types of, or developing new different type of algorithms for different sorts of application, whether this is for image-based applications or unstructured-based type of modeling, to be able to speed up and accelerate some of the bottlenecks, especially for computational time, more amount of human-intensive efforts that need to be put in place for sorting these type of problems.
Along with the code, do you also publish a data set to support folks researching in this area, or are there well-known or already existent data sets in this space?
The good news, there is a lot of kind of open source data sets available for that. The beauty about this approach is enabling people to actually take these kind of generally publicly available feature set of physical properties and converting them into these kind of texture-based images to try to apply our architecture for these type of problems. And this is actually a common challenge that facing most of the previous research in this area, how you can use a very kind of a sparse representation of non-homogeneous feature set. So the correlation usually between these geological features is very crucial to be able to correctly predict what type of facies that expected as an outcome. And using this kind of an image-based approach for training, take some this kind of deficiency or limitation out of the equation.
Given how important the image creation part of this is, the Fourier transform, is that specific code that you're providing in the repository as well, or is it something that you just need to explain how to do it, like, run your data through, MATLAB's FFT, routine, or presumably you have to tell people how to do that part also?
Right, and this is actually, in our situation, we recommend people to use the standard techniques that's being described in the paper, because this is part of the feature pre-processing, like data pre-processing, and it varies from one type of a problem domain to another. So for example, if we're trying to apply this for example, sensor data that's coming from satellites or vibration data that's measured over time, then it might require a different type of parameterization for that short time for your transformation to be able to generate the same representation of important features. Sometimes,
but doing it is not a mystery.
Exactly.
You just explain how it can be done.
It's a standard process.
But it sounds like you can apply this general technique beyond geological sciences to a bunch of other areas. Can you talk through some of the examples you just mentioned?
So one of the other examples we kind of also envision using this for is for any type of equipment kind of abnormality detection. A common example for that, if you have an equipment that have different types of vibration rate over time, then usually you would have a sensor measurement over time for how that vibration signal is being captured. And if you actually convert that using the Fourier transform, you would be able to generate an image representation for how that kind of vibration feature look like over time. And being able to use that as a representation input for model development is also a possibility.
Yeah, I would expect for this kind of, for like this predictive maintenance thing we're talking about, where we have a time series of, sensor readings, that the FFT part of that would be fairly standard, right? To get a frequency domain feature. But the image part of that is the part that I'm still trying to wrap my head around a little bit.
If you think about the main issue with any type of kind of anomaly detection is usually the difficulty of determining what constitutes an anomaly, because over time there might be a concept drift from what is normal, but that still haven't actually materialized to the point of being an anomaly. So it's kind of a continuation. Being able to actually represent that kind of change in the distribution over time would give you a different kind of representation for how things really evolve before you can actually use a static threshold of determining by exceeding that type of an upper boundary, you already fall into that space. So it's I'm not saying that's the only way of doing it, but if you want to, for example, to account for normal variation within the boundary before it reach an extreme outlier level, then that's a way of attenuating that signal to noise ratio to make it more useful and more generalizable as well.
And so from that perspective, is it fair to think of the spectrogram as, not so much you're processing an image, but you just have a bunch of vectors of frequency components relative to time?
That's actually a fair representation, exactly. Okay. And really what you want it to do is you want to representation that time frequency domain in a more kind of an image kind of structure to be able to determine which part of that image is more relevant, more salient to provide more informative feature set for training your model.
Yeah, I'm still struggling with like when I think about an image, I'm thinking about things like convolutions that are taking, that are operating in kind of multiple dimensions and kind of aggregating and things like that. How does that play out in the RNN scenario? Or does it play out in the encoder scenario? I guess it plays out in the encoder. Right. Okay,
and if you think about it, these are images that's captured over multiple period of time. So that kind of depth-based is reflecting, taking an image, a shot at each kind of depth-based approach. So you can have, every half a feet, you would have a different image generated, and you would be able to see a transition as if you're having a moving object from point A to point B.
Got it.
Every time you take a shot, that frame would represent a moving aspect or an adjustment to the image that's being captured.
That makes sense. Thank you for helping me get there.
Thank you.
I'd love to hear you kind of talk a little bit about some of the other things you're working on there. I've had your colleague Dan on the podcast a couple of times, talking about some of the work that you're doing in the platform space, and you attended the TWIML AI Platforms Conference, kind of in furtherance of that. So clearly you're building platforms to support lots of different things. What are some of the other things that you're working on there?
I'm glad you actually raised that question. I think people typically, when they think about how you operationalize these type of models, they think about maybe I'm getting a very kind of high accurate model. It's performed very well on my training data and testing data set. But we actually very kind of thinking about and very focused on the idea, how do you make sure this is deployable and is scaled to a large application use? And that's why we kind of designing and building this kind of expandable open architecture platform based on Kubernetes to be able to actually commissioning the same type of development and training environment and being able to push it to different types of deployment mechanism. Currently, we have ways of deploying models within, for example, our central data warehouse, or typically we push things to the cloud. We have a very large distributed kind of an environment for hosting these applications. But the key ingredient here is, how do we actually go from point A to point B? Because in order to be able to provide real insights in a very timely manner, the amount of data acquisition and data transformation is very crucial to be able to handle in a more systematic way. And that's why all the pipelines and feeding of our crucial kind of feature sets that's required for any type of a model is something we spend quite a bit of time of designing, building, and making sure that everybody have the access to this in order to be able to using it in a day-to-day operation. Mm-hmm. So that's the primary essence of designing the platform. One of the things we're also very passionate about is how we can right now have a very large kind of a library of models that's actually reusable. Mm-hmm. We hardly tend to start things from scratch. We have a library of dealing with things about ingesting large amount of different types of data structure, whether it's time series or unstructured or large seismic volumes and so forth. And then being able to very quickly scale these up and run them in a massive parallel. I think the largest kind of number of models, we have about close to 500,000 models for different predictive subsystem units across the whole organization being running in real time.
Wow. Wow. So someone could go to some catalog and choose FaciesNet and just drop it into a pipeline somewhere?
Exactly. So they will specify, for example, what is your feature set look like and where it's actually located. Mm-hmm. You specify, for example, the volume that you're going to be trained on, and that would give you some recommendation about what kind of GPUs you would require, and give you also an estimate about what time it actually take to complete that job. Okay. And we're putting that in perspective as a benchmark for what is a conventional approach and workflow would take typically. And I think we're very pleased to see that we're making a significant amount of progress on reducing that cycle time.
I also saw that you announced the AI Fellows program. Can you talk a little bit about that?
Yes. Actually, our Shell.ai residency program is one of the exciting programs we're happy to announce recently. This is actually one of the programs we announced last year in NeurIPS. Mm-hmm. We happily now have our first cohort of AI residents being on board. This is a 2-year program where we invite people who are PhD or postdocs or some people with a significant amount of experience, industry experience in machine learning and AI to come and work with us across different type of challenging problems, basically defining what is the next wave of solving these challenging problems, whether this happen to be in the energy space or like in how the whole energy transition, new parts of the business, to be able to work on these problems for 2 to 3 different rotations. So currently we have people who are working on the hydrogen business, how we optimize the generation of hydrogen across the whole our new energy platform mix. People who are working on very interesting projects in the exploration side, people working on the trading and asset optimization, people work on predictive maintenance. And the goal here is it's a 2-way collaboration. It gives people the opportunity to shape the direction and innovation within machine learning application across different types of domains. But at the same time, we provide enough training, challenges, and support for people to publish, collaborate, and openly challenge the status quo of how we do things.
You said you have your first cohort in place. Are you out there recruiting your second cohort?
And actually, we currently very actively are looking for the brilliant minds to come and join us. So always welcoming people in our space. And we encourage people to check out Shell.ai residency program on our Shell website. Very kind of interesting. We have a lot of Q&As and a little bit kind of videos about the existing residents, what they're working on, and what's their experience so far.
Awesome. Well, Mohamed, so great to catch up with you as always. Any kind of parting words about your experience thus far at NeurIPS? We're just kind of getting started, but
it's an amazing. Actually, the last couple of days I've been very fortunate to participate in different affinity groups. Actually, this year also we're sponsoring Women in ML workshop. Okay. But actually, I had a chance to stop by Black in AI and other type of affinity groups. It's really interesting. Lots of interesting ideas. The poster session yesterday was fantastic, and I'm looking forward to actually spend the next few days and getting to see more about these kind of outstanding ideas coming through.
Awesome. Same here. Well, thanks once again.
Thank you, Sam. Really a pleasure talking to you.
Thank you. My pleasure.
Cheers.
All right, everyone. That's our show for today. For more information on today's guest or our NeurIPS podcast series, head over to TWIMLAI.com/NeurIPS2019. Thanks once again to Shell for sponsoring this week's series. Check out the Shell.ai residency program by typing shell.ai into your browser's address bar. Thanks so much for listening. Happy holidays, and catch you next time.